Hi everyone and welcome to Lab 1. Exponential growth is the topic of this lab, and we're going to cover exponential growth using three different tools. We're going to use first Excel, which hopefully many of you are already familiar with, and we're also going to model exponential growth using R, and we're going to use Insight Maker. So these are the three tools we're going to be using throughout the semester. So I thought it would be a useful way to introduce you not only to the most basic concept of population ecology, that is exponential growth, but also the three tools that we're going to be revisiting and using throughout the semester. So before we get into the modeling though, what we need to do is go over the mathematics. Now, this isn't necessarily the thing you're most looking forward to in the class, but going over the mathematics is obviously a critical part of population ecology. It has been from the very beginning. This is a mathematical discipline. To understand and to model populations, we have to work with numbers. And so last year when we started going over this lab, we were in person still at that time. One of the students, as soon as I said we were just about to go through the mathematics, she said, "Yay!" And it started to become a kind of a running joke throughout the semester. Whenever I said, "Okay, now it's time to go through the mathematics," people would say, "Yay!" So it is now time to go through the mathematics. All right, let's do it. I encourage you all to go through the PDF or the website and work through the mathematics on your own, but let's work through it together using the whiteboard. Oops. All right, so the first thing we need to do when we're going through the very basics of population ecology is to define the population. And the population we define as N. All right. So N is the number of individuals in the population, and oftentimes you'll see a little t there to represent the time. So the population at time t was, say, 100 individuals or 10,000 individuals. So there we go. We have the population size, and there's only a few different processes that we can think of that could potentially change population size. So we're going to draw some arrows going in and going out of this population N. Let's draw an in arrow, and you can imagine what this might be. Maybe the most obvious thing that it could be is births going into the population. So we'll define births as big B. That's the total number of individuals born into the population. Sometimes you'll see a sub t. That's the total number of individuals born into the population at time t. Let's draw an out arrow, and you might guess what this one might represent. This is D for deaths, or dt, the number of deaths in the population at time t. So we have births and deaths. And there's a couple other processes we might think of. If you start to scale up back a little bit and think that there might be other populations around, that maybe this population that we're representing here by N isn't the be all and end all. There might be other populations around, and there might be immigration and emigration that affects the number of individuals in this population. There might be immigration coming from outside. I'll draw an in arrow, and I'll represent that as big I. And there might be emigration. I'll represent that as big E. And that is, we could also put sub t there if we want. And now we have really all the major processes that could change this number N over time. Births, deaths, immigration, emigration, and we can write this out as an equation. We can write delta N. So delta N meaning the change in population abundance over time. One way we could do that is say delta N is N at some time t plus 1 minus N at time t. So that's the change in population abundance over some time period, all right? So change in population abundance over some time period is defined as delta n. That means a change in population abundance, and there's only 4 things that could potentially change the population abundance. Those things are B, D, I, and E. Let's write them down. We have births plus immigrants minus deaths minus immigrants, and then we have this equation, which is, some would consider, the most fundamental equation of population ecology, sometimes known as the BIDE equation, BIDE, and that is a good place to start when we're going through the mathematics of population ecology. All right. Now, what we tend to do in population ecology is we tend to ignore the immigration and emigration, at least at first. It simplifies the process of thinking about populations and how they can be sustainable without having to think about immigration and emigration. So let's just imagine a closed population. A closed population has no access to other populations around. There's only 2 processes that can change the abundance in this population, and that is births and deaths. So let's simplify our population model here, and we can say that delta n is now equal to births minus deaths. All right. Now the next thing to think about, and I'm going to go back to the lab for this. Now this equation, delta n equals b minus d, it makes a lot of sense. The issue is that b and d aren't really constant. The bigger the population is, the bigger you'd expect B and big D, the total number of births and the total number of deaths. And you can imagine, a population of size 10 and the total number of births in that population versus a population of size 1,000 and the total number of births in that population. Obviously, the total number of births is going to be bigger in the population of 1,000. Why is that? Well, because every individual, every reproductive individual anyway, is going to give birth to, on average, a particular number, such as 1.2 or something like that. So every reproductive individual, every reproductive female should be able to give birth to a certain number of individuals. The more individuals there are in the population, the more total births you're likely to see. So what's the number that's likely to be constant for the population, or at least something that we can imagine could be considered a constant? That would be not the total number of births, but it's the total number of births per reproductive female, right? That should be somewhat constant. No matter what the population size is, perhaps, we can think of, or at least assume in this very simple population model, that every female in the population, whether the population is really small or really big, every female is capable of giving birth to, on average, 1.1 offspring per time step per year or something like that, right? So we have to start thinking about per capita rates, not the total number of births, not the total number of deaths, but the per capita birth rate and the per capita death rate. So it's really important to start thinking about per capita rates. So let's think about how we can, in plain English, talk about per capita rates. Here are some examples. For every individual in the population right now, we expect 10% to die in the coming year. 10% is really a per capita death rate. We're talking about like every individual. So if there's 100 individuals, there's going to be potentially 10 deaths. If there's 1,000 individuals, there's going to be potentially 100 deaths, right? 10% death rate. For every individual in the population now, we expect 0.8 new juveniles to enter the population in the coming year. That's a per capita rate. For every individual in the population, already we can tell it's a per capita rate because we're talking about something that's true for every individual. And all we have to do to think about what the total population number of juveniles entering the population is to just multiply this per capita rate by the total population size. And so that's the basic idea of per capita rates. Here's some more examples. For every female in the population now, we expect 1.1 offspring to be born into the population in the coming year. For every individual in the population now, we expect 3% to be harvested in the coming year. So we can even think of per capita harvest rates, for instance. For every juvenile in the population now, we expect 34% to disperse away in the coming year. So we can even think of immigration and emigration using per capita rates. It generally makes sense to think about per capita rates rather than the total number of individuals leaving or entering the population. So let's go back to our whiteboard and start thinking now about per capita rates. The per capita rates that we usually talk about and represent mathematically in population ecology are the lowercase versions of these uppercase letters here. So we're going to define the per capita birth rate B, little b, as equal to big B divided by n. That is the per capita. So to get the per capita rate, we just divide by the total population size. So we get the per individual rate of births in this case, and we define that as little b. We can also define deaths, little d, the death rate, as the total number of deaths divided by the total number of individuals in the population. So if there's 10 deaths and there's 100 individuals in the population, we have a 10% death rate. All right. So these are more fundamental constants that we're going to be working with in this lab and in the course all through the semester, are these little lowercase rates like the birth rate and the death rate. Let's define, we can just rearrange these equations to define in terms of what big B is actually. Big B is we just multiply both sides by n. Big B is equal to the per capita birth rate times the number of individuals in the population, right? Just the same way, big D here is equal to little d, the per capita death rate times the total number of individuals in the population. And we can go even a little further here. So now we've defined big B and big D in terms of these more fundamental constants for a population: per capita birth rate, per capita death rate. Now we can go back to define delta n, which we already defined as the total number of births minus the total number of deaths, right? We can take that, but now we can replace the big B with little b times n. We can replace the d with little d times n. So now we have little b times n, that is delta n is equal to little b times n minus little d times n. Now we can easily just factor this out here, like this n occurs in both of these terms. So another way of representing this same equation is just saying b minus d times n. All right, now both little b and little d are per capita rates. We've said that they're kind of something we can assume to be constant for the population. The per capita birth rate, per capita death rate doesn't really depend on the population size, at least in this very simple model. And so both of those are constants. What can you do with two constants that are being subtracted? We'll just make that a new constant. And so this will make a new constant. We can define this constant as, oops, didn't mean to do that. We can define that constant as little r. So little r is equal to b minus d, and then we can rewrite this equation as delta n is equal to little r times n, which really is the most fundamental equation of population ecology. So this is something you really should commit to memory. Delta n, the change in the population over a given time period, is equal to this constant r. Now little r is a constant that is often called the intrinsic rate of population growth. So again, a fundamental constant that we can use to think about populations. Populations with a larger value of R, or the intrinsic rate of population growth, obviously have a faster rate of growth. Lower values of R have slower rates of growth. And there's a critical distinction here between populations that are growing and populations that are declining. And we can look at the R value and immediately determine whether a population is growing or declining. If R is greater than 0, then births outweigh the deaths and the population is growing. If R is negative, if little r is negative, then deaths outweigh births and the population is declining. All right. One more thing I wanted to go over is now actually getting a little bit into calculus. I don't need you to understand exactly how this all works, but there is a really important distinction to make between continuous population growth on one hand and discrete population growth on the other hand. We're going to go through both types of population growth, but to represent continuous population growth, that is, the population is growing continuously no matter how small you slice the time frame that you're thinking about, there's still some amount of growth in that time frame. That's continuous growth. To represent that type of growth, we need to use calculus, and we can represent this very same equation right here as continuous growth. And let me just write this out. So here we have continuous growth. It's very hard for me to write this out using a mouse, but continuous growth on one hand, and we can represent it as dn dt, that is the rate of growth over an infinitesimally small amount of time. Dn dt, the instantaneous rate of growth, is defined as r times n. So this is the exact same equation, just represented now using calculus. So you'll see the fundamental equation of population ecology written this way frequently. And we can go a little bit further and we can integrate this, which means that we will take this equation about how the population is changing over time, and we're going to basically add up that growth over this entire time period in order to understand how many individuals were in the population at one time, and then to figure out how many populations are how many individuals are in the population at the end of this whatever time frame we're integrating across. And so don't worry about how this integration works, but do commit this to memory. So we have another equation to memorize, and that is this equation represents the population size at time t as a function of the population size at the initial time. So whenever the start of the period we're interested in, maybe the population at time 0 is 100, and we want to know what the population size is 50 years later. All right, so then we have to say, take the initial population and then take the base of the natural logarithm and raise that to the r times t. R is just the intrinsic rate of population growth, and t is the number of time steps that we wish to estimate the population size in the future. So this is the equation that we can use to represent the population size after a certain number of years. For instance, we have a starting population size, we have an intrinsic rate of growth, and we have the number of years that we want to model. All right, let's just run through this equation really quickly in R, just to give you a hang of not only using this equation, but also using R. And in this case, we're kind of using R just like a calculator. So we're going to calculate, I'm just using this pound sign just represents a comment. It means that R is not going to think about it or trying to make sense of it. It's just for us humans to make this code readable. So I'm just going to write something like, let's calculate population size using the basic exponential growth equation. All right, so what do we need? We need N0. That's the initial population size. Let me just say, let's say that's 100. We need the intrinsic rate of population growth. Let's say that's 0.03, just making something up. And what else do we need? We need the number of years that we want to estimate the population at, say, 50 years later. Let's just write that in, 50. So if we read in these values, then we can calculate the population size at time t. I'll just call it NT, and we'll take the initial population size and then multiply it. I'm just going to use the asterisk to multiply it, and then I'll use this exp function, which just takes the natural the root of the natural logarithm e and adds and puts that e to the power of whatever you put in this parenthesis, and that's going to be r times t. So I'll run that equation, and let me just write out this nt, the variable that I just defined here, and if I highlight that and hit Control Enter in RStudio, it'll just spit back the number that is represented in this value, this variable nt. And so I have 448 individuals after year 50. I started with 100. I had a growth rate of 0.03, and I estimated the population size after 50 years, and after 50 years the population is now 448. All right, so that's basically how we can use this equation. Don't worry if you didn't totally follow along in R, but I do suggest maybe trying it. Just open up RStudio and see if you can replicate this. This is a pretty simple thing to do in R, and it can help you understand the fundamental equation that we're working with here, and also help you get started working in R. So that is an important equation, and this obviously is a very fundamental equation. And there's a couple more equations I just want to introduce you to, and this has to do with another way to think about population growth. Right here, we're thinking about continuous population growth. That is, the population, no matter how small the time slice you're thinking about, the population's always growing, all right? So no matter, even if you're talking about a second, 10 minutes, a month, a year, there's some population growth happening in that time period. So population is growing continuously. And for continuous growth, we use calculus to model population growth over time. Let's think about let's think about discrete population growth. So discrete is the other way we can model population growth. Discrete population growth. And what do we mean by that? Well, what we're doing here, let me just get myself a little more white space here, and I can represent discrete and continuous growth graphically. Let's just do that here, and I'll represent continuous. In both cases, we're modeling population growth or abundance over time. So we have abundance on the y-axis, and we have time on the x-axis. And the continuous growth model that we just talked about is going to look something like this. Like, no matter how small the time frame, it's going to be a little bit of growth, and it might start accelerating. And we have this exponential growth process over time. But again, no matter how small you slice this time step, it's going to be just a little bit of growth in this area. All right, so that's continuous growth. Discrete growth looks more like this. The population stays constant, and then it jumps up. It stays constant, jumps up. Stays constant, jumps up. Stays constant, jumps up. And you can still see kind of an exponential growth pattern here. But the difference here is that the population is jumping up only at particular points in time. This is called discrete growth. And both types of models, this discrete model and this continuous model, are extremely useful in population ecology. And both of these can be called exponential growth. You can see the growth increasing as the population size increases. The growth increases. Same here, as the population size increases, the rate of growth increases, right? But they're just two different ways of representing exponential growth. And we're going to represent both types of exponential growth in this lab, all right? So we have to understand both types of growth. So let's now think about discrete population growth. Now, the most fundamental constant for discrete population growth isn't little r, the intrinsic rate of population growth, but it's called lambda. All right. So again, you'll see this again and again in population ecology. There's this term called lambda, which is called the finite rate of population growth, or the discrete rate of population growth, and it represents the population at time t plus 1 divided by the population at time t, which is basically, it's the number that you have to multiply the abundance at time t in order to get the abundance at time t plus 1. It's just a multiplier. It says take the population at any given time, multiply it by lambda, and you get the population at the next time step. All right? So another way to represent this is, say, population at time t plus 1 is equal to the population at time t times lambda, right? So this is a pretty fundamental equation that you definitely should commit to memory, all right? And the population at size t plus 1 times the population at time t plus 1 is equal to the population at time t times lambda, lambda being the finite rate of population growth. All right, before we end, and we're very close to finishing up here, let's first of all go over the difference between discrete and continuous growth. This is a really important distinction, and it's not always the easiest distinction to make. So let's just, again, in plain English, go through a few examples of discrete and continuous growth rates, or population rates. And so let's think about little b in the continuous growth model, right? Babies enter into the population at a rate of 0.9 per adult female per year, but the pool of babies is distributed evenly throughout the year. That is, any time frame that you're thinking about in this population, even a really tiny time frame, there's going to be some births in the population. All right, the births are just distributed evenly across time. All right, now let's think about the discrete birth rate. So we can think about little b sub d. I'm just calling that, and this is the way Gatelli does it as well. Little b sub d is the discrete birth rate, the discrete per capita birth rate. We'll say babies enter into the population at a rate of 0.9 per adult female per year, just the same way as we represented up here. But this time, the pool of babies enters the population simultaneously on, say, April 1st every year. So that gets us this kind of like jumpy growth rate that we just saw here, this rate here. At April 1st every year, you have this like pulse of births entering the population, and otherwise there's no births at all, so the population stays somewhat static. So that kind of illustrates what we're talking about. Let's go through a few more examples. Let's think about the per capita death rate, but this time with the continuous growth model, little d. Approximately 23% of the population dies each year, but the deaths occur evenly throughout the year. So no matter how small a time window we're thinking about, there's always going to be some deaths occurring. It's spread out evenly throughout time. Let's think about the discrete rate, death rate, little d sub d for discrete. Approximately 23% of the population dies each year, just the same way as up here, but all the deaths are assumed now to occur, let's say, on January 1st each year. All right, so now the deaths occur only in these pulses at one time per year. And obviously these are simplifications that we're making to represent populations, but that's what we're always doing in this class. We're making simplifications to represent populations. We have to choose whether to represent the population as a continuous growing population or as a discretely growing population. And we can think about R as well, the intrinsic rate of population growth. We can think of that, usually we think of it as a continuous rate. So the population is growing constantly or continuously at a rate of 15% per year, for example. And this can be somewhat confusing because you can see that R, little r, just the intrinsic rate of population growth is, say, 15% per year, right? So the little r is already in units of per year. So, okay, you're going to expect that the population should grow exactly 15% over a 1 year period. But since the population is growing continuously, the rate of the actual growth rate of this population is going to be a little bit higher than 15%. In fact, it's going to be 16.2%, which is computed using this equation down here. So you just have to take e, or the base of the natural logarithm, to the r, that is the intrinsic rate of population growth, to be able to get lambda, and that is the actual amount by which the population grows over, say, 1 year period. Now, don't feel like you have to understand this right now. This concept is a little bit confusing, but hopefully after the end of this lab, after you've had a chance to work through these concepts yourself in Excel and in R, then hopefully it'll be more intuitive, or you'll start to make sense of this. And this is something we'll talk about more later. And we can now think about the discrete rate of population growth. And this is simply the population size 1 year from now would be 15% higher than it is today. So if little r is 0.15, then the population 1 year from now is literally 15% greater. All right, because this is how discrete growth works. It just pulses up. When we look at this, we see, okay, here's year 1. Next year, the population's 15% bigger. Next year, population's 15% bigger, and otherwise it stays completely flat. Exactly 1 year later, the population jumps up. And so discrete growth is in a way easier to work with, easier to understand, and in fact, that's mostly what we're doing in this class. We'll use discrete population growth to represent most populations just because it's easier for us to work with. It's a little easier to understand. It's a little easier for computers to implement these models. So this is mainly what we're going to be working with, but it's really important to know both types of population growth, and in some cases, you might want to represent your population as a continuously growing population, right? Before we end, I just wanted to go back to the discrete population growth one more time and build out a model that's analogous to this model here that describes the population size in the future, at some time t in the future. All right. So this is how we do it in a continuously growing population. Now, for a discretely growing population, we're going to represent it in a slightly different way, and we can build it out just by using this equation here. We can say, okay, at time t plus 1, we start with the initial population size and multiply it by lambda in order to get the population size at time 1. All right. So another way to represent that is just to say, okay, the population size at time 1 is equal to the population size at time 0 times lambda. All right. What about the population size at time 2? So we can say, okay, population size at time 2 is equal to the population size at time 1 times lambda, right? But the population size at time 1, we've already defined it, so we can replace that with population size at time 0 times lambda. So the population size at time 2 is the population size at time 0 times lambda times lambda. What about the population size at time 3? Now we can take the population size at time 2 and multiply by lambda. So now we have n0 times lambda times lambda times lambda. You can see what's going on here. All we have to do in order to get the population size at time t is to take the population size at time 0, multiply it by lambda to the tth power. So if you want to get the population size at time 5, you just take n0 times lambda to the 5th power. All right. Now, this is another equation that you should commit to memory. So now you have how many equations? 4 equations here that I would like you to commit to memory. They're fairly simple. Hopefully it's not going to be too burdensome to commit these to memory, but they're really, really that important. So here's the change in population size is equal to the intrinsic rate of population growth times n. You have the population size at time t is equal to the initial population size times e, the base of the natural logarithm, to the power of r, intrinsic rate of population growth, times t. In a discrete population, the population size 1 year from now is equal to the population size now times lambda. And the population size at time t is equal to the initial population size times lambda to the tth power. All right. So those are the basic equations of exponential growth. All of these equations represent exponential growth, and we will explore these equations more in lab today or this week. And let's just quickly go into R and run through the discrete population growth. I almost wrote population. Population growth. All right. So again, we need the initial population size, n0 equals 100. R, well, lambda is what we really need. Lambda is equal to, and I'll just say 1.03, which is analogous to the growth rate we have up here. This little r of 0.03 represents a 3% growth per year, and this lambda, 1.03, if you multiply a population by 1.03, you basically have 3% growth. So lambda is 1.03, and t is equal to 50. So let's write out our discrete population growth. So nt is going to be equal to n0 times lambda to the power of t. I'm going to read those in, and let's look at what nt is. It's 438. What was it back here in the continuous case? It was 448. So you can see that the population size was a little bigger after we calculated the continuous, the growth after 50 years using a continuous growth model, versus it was a little smaller when we computed population size after 50 years using the discrete population growth model. All right. So that's a little sneak peek into what we're going to find in this first lab 1. All right. The next thing we're going to do, I'm going to end this video now, but then we're going to go through exponential growth. I'll do a little demo in Excel first. All right. So I'll see you then.